This is section 4.3 notes for pre-calculus. And today we're going to talk about graphing some different kinds of graphs that we haven't done before. These are called rational functions. And all that means is they're going to be equations that look like fractions. But the thing about the fractions is these fractions, these fractions are such that they're going to have x's in it. Maybe x's in the numerator, maybe x's in the denominator, or both. Okay. So first of all, we need to talk about what these graphs can look like. It says, for what values of x is the function below not continuous? Okay. So as I jump on the graph, let's say I jump on it over here on the far left, and I start moving my eye along this graph. As soon as I get right here to where x equals 2, you can see that there's a hole in the graph. And so that means that this graph is not continuous. I'm sorry, -2. That means this graph is not continuous at -2. If I keep going along the graph, moving this direction, do you see that when I get down here to the bottom, I have to kind of pick up my pencil in order to jump back up here to the top? The two pieces of the graph are not connected, so that means this graph is not continuous at x equals 1. And if I keep going over to this point, the graph stops, and then there's a gap before the graph picks up down here. So that means there's another discontinuity at x equals 3. Okay, so these graphs that we're getting ready to do might have asymptotes, they might have holes, they might have just, weird stuff that we're not used to going on the graph. Okay, so discontinuities occur when the function is undefined. Okay, discontinuities occur when the function is undefined, but remember, a function's undefined whenever the denominator equals 0. So there's going to be two types of discontinuities: holes and vertical asymptotes. Okay, holes and vertical asymptotes. So first of all, let's talk about holes. Okay, you'll always know when you're going to have a hole on your graph, because that happens whenever you have factors that cancel. Factors that cancel. So for example, when I look at this particular function, I'm going to factor both the numerator and the denominator. So the numerator is going to become, let's see, x plus 3 and x minus 1. I think that'll work. There's nothing I can do in the denominator. So do you see that the x minus 1 is going to cancel with the x minus 1? So there was a factor of x minus 1 that canceled, and that means what I have left is just simply x plus 3. Okay, well, like we said, if there's a factor that cancel, that means you're going to have a hole on the graph. So the graph has a hole when x equals 1, but if there's a hole when x equals 1, I kind of need to know what the y value is to know where the hole is, because here's where x equals 1. Is the hole up here? Is the hole down here? Where is that hole? So I need to know what the y value is. So in order to find the y value, you take that x equals 1 and put the 1 in for x over here in your simplified version. If I put a 1 in for x, I'm going to get a y value of 4. So that means this graph is going to have a hole right where the point 1, 4 would have been. Okay. So let's talk about graphing this particular function. So I know I have a hole, but how do I know what the rest of the graph looks like? Well, the simplified form of the equation was just y equals x plus 3. Well, if it's just y equals x plus 3, isn't that just the equation of a line, right? Think of it as mx plus b, y-intercept of 3, a slope of 1. So you might say up 1 over 1, that'll hit the hole. Or you could go this direction, right? A slope of 1. So when I draw this line, yeah, it goes right through that hole. But the fact that there's a hole there means that there's like a little space in the graph at x equals 1. Okay, so in this case, you had a hole, but it was the graph of a line. So all rational functions don't turn out to be lines. They could be anything that might have holes or vertical asymptotes. Okay, so that's the idea of a hole. So let's go on to talk about the idea of a vertical asymptote. Okay, well, once you've done your factoring and you've canceled everything that can cancel, then you'll know you have vertical asymptotes whenever the denominator equals 0. So anything that's left in the denominator could equal to 0. So when I factor this, I can't do anything with the numerator, but the denominator could be x plus 4 and x minus 1. Nothing cancels. That means there are no holes. Okay, but what about vertical asymptotes? So you look at the denominator. There's an x plus 4 factor and there's an x minus 1. Well, the denominator would equal 0 either if x equals negative 4 or if x equals 1, right? Those are two places that would make the denominator equal 0. So that means that these are your vertical asymptotes. And one thing to notice is that for vertical asymptote, there's no such thing as going in and finding the y value because these represent vertical lines, right? And remember back in the day, we said vertical lines are always written as x equals a number. Okay, so let's kind of put it all together. Again, we're not doing any graphing yet. We're just talking about how to find those holes and how to find those vertical asymptotes. All right, so look at the first one. So we definitely need it to be in factored form. So factored form would be, let's see, x plus 3 times x minus 1 all over x minus 1. I think that's going to work. So I think you can tell that the x minus 1s are going to cancel. What that tells me is that there's a hole when x equals 1. And so whenever this cancels, all I have left is the x plus 3. So if I want to find the y value, I'm going to put that 1 in for x over here. I'm going to put it into this simplified equation. And so in this case, the y value is 4. Okay, what about, are there any vertical asymptotes? Well, notice in my simplified version, there's not even a denominator. Well, if there's no denominator, then there can't be any vertical asymptotes. Okay, so let's look at letter B. Again, the first thing I need to do is get it into factored form. So I'm going to think of this as, can't do anything with the numerator, but the denominator would be x plus 4 times x minus 3. Okay, so in this case, nothing's going to cancel, and what that means is there are no holes. But what about vertical asymptotes? Well, again, this has two factors in the denominator. So the denominator would equal 0 either when x equals negative 4 or when x equals 3. So there are two vertical asymptotes. Okay, and let's look at the last one. We need to get it in factored form. So let's see, x minus 3 times x plus 1 and x minus 3 times x plus 2. I think that's going to work for both of them. In this case, I do have something that's going to cancel. So let me just scooch this over here a second. And what I have left after my canceling is the x plus 1 on top and the x plus 2 on the bottom. So I have holes from that factor that canceled. That's going to be when x equals 3. So again, if I want to find the y value, I've got to take that x equals 3 and plug it into my simplified version of the equation. Everywhere I see an x, I need to put in a 3. So I'm going to end up with a 4 over 5. Yeah, it might be a fraction. We can estimate if we have to graph it. And then for my vertical asymptotes, well, do you see that there is still a denominator, x plus 2, and what would make that equal 0 is if x were equal to negative 2. So what I was trying to show here is it might be that you have a hole but not a vertical asymptote. It might be that you have no holes but you have multiple vertical asymptotes, or it might be that you have both holes and vertical asymptotes. You can have multiple of both or none of both. Okay? So that's vertical asymptotes. There's also horizontal asymptotes. And just to kind of give you a refresher, remember when we were doing parent functions and we talked about, hey, if you have the graph of y equals 1 over x, remember how for 1 over x, we said, okay, you've got a horizontal asymptote and you have a vertical asymptote. And then we would use those asymptotes to basically draw the rough sketch of our graph. Okay, so what if it's not just a basic 1 over x graph? You know, what if it's who knows what the equation might look like? And what if it's not something that I'm familiar with as a parent function? Well, you could still have horizontal asymptotes. Okay, horizontal asymptotes describe the end behavior of a graph. Okay, horizontal asymptotes describe the end behavior of a graph. So what I mean by that, remember my 1 over x graph? So there was a horizontal asymptote at 0. What that means is as you go way far out to the end of the graph on the right, do you see how this graph levels off at y equals 0? Or as you go way far out to the left end of the graph, this levels off at y equals 0. So it's telling me what happens at the end of the graph, not necessarily what happens in the middle of the graph. Okay, so horizontal asymptotes describe the end behavior. In other words, a horizontal asymptote shows where the y values level off. Okay, this shows where the y values level off as the x values get increasingly large, meaning as you go out to the right side, or as the x values get increasingly small, meaning you're going out to the left side of the graph. Okay, so how do I know what the horizontal asymptote is? By just looking at the equation, not the graph, but by looking at the equation. Well, it all comes down to the degree of the numerator and denominator. And remember, the degree is the highest exponent. We talked about that the other day. The degree is the highest exponent. So you compare the highest exponent of the numerator to the highest exponent of the denominator. Okay, so if you have an example, let's say you have the example y equals x plus 2 over 3x squared minus 5. Okay, well, I can tell that the degree of the top is 1, right, because it's next to the first. The degree of the bottom is 2 because you have an x squared. So the degree of the top of the numerator is less than the denominator. This is our first case. In that situation, the horizontal asymptote is y equals 0. Okay, but what if you have the opposite? Like what if it's y equals x squared minus 7x, and on the bottom, maybe you have a 5x plus 1. So in this case, do you see that the degree of the top is 2? The degree of the bottom right there is 1. So the numerator has a higher degree than the denominator. In that case, for horizontal asymptotes, we would say there are none. So hopefully you can tell the only other option is what if the degree is the same? So what if I have, like, let's say y equals 3x squared plus 2x all over 5x squared minus 7. So do you see that the degree of the numerator is 2 because of the x squared? The degree of the denominator is 2 because of the x squared. So the degrees are the same. In that case, we would say y equals, basically it's the leading coefficient from the top over the leading coefficient from the bottom. Okay, and so in this case, it was 3/5. I guess I should have said generically, you're going to take the coefficient from the numerator over the coefficient from the denominator. But like I said, on this one, it's going to be y equals 3 over 5. And when I say the coefficient, I'm not talking about that 2 and 7 at the end. I'm talking about the leading coefficient, right? That's the number in front of that highest degree term. Okay, one thing I want to point out, keep in mind, a graph will never cross a vertical asymptote. A graph will never cross a vertical asymptote, but, and I'm sorry this got cut off, but you need to put it in, but it can cross a horizontal asymptote. Okay, so like for example, maybe you have a horizontal asymptote right here at like y equals 1. It might be that your graph, as you're going way far out to the right, it might be that your graph is leveling off right there at 1. But who knows, maybe in the middle it crosses over, and then as you go out to the left, it comes back down and crosses over. So again, the horizontal asymptote is about what happens at the end of the graph. It's not necessarily about what happens in the middle of the graph. Okay, so let's just practice. One thing I do want to give you is there's this acronym that a lot of teachers will teach, and I'm not really big on cutesy little acronyms and stuff like that, but because it is so universal, I don't really know any teacher out there who doesn't use it. because it's so universal, I want to show it to you just in case you're, in another class somewhere and they mention it, okay? The acronym is called Bobo Botten. I know it's stupid. Eats DC. Bobo Botten eats DC. And usually when I hear people refer to this, they'll say, "Oh, Bobo Botten." They kind of forget about the eats DC, which is fine. Whatever helps you to remember. Once you do it a few times, you'll kind of remember. So the Bobo means bigger on bottom. Okay, let's see, bigger on bottom, meaning the degree of the bottom, the denominator is bigger. And in that case, we're saying that the horizontal asymptote is 0. You can probably tell now the BOT, Botten, means bigger on top. Whoops. I'm trying to keep this color coordinated. Sorry about that. Okay. Bigger on top. Okay, bigger on top means there are no horizontal asymptotes. No horizontal asymptotes. And the eats DC means exponents are the same. EATS, exponents are the same. And then the DC means divide coefficients. Okay, so let's try to practice that. So look at, I'm going to come back to letter A. Let's look at letter B first. Okay, do you see that the degree of the top is 1 because it's next to the first. The degree of the bottom is 1 because it's next to the first. So that's the exponents are the same. So the horizontal asymptote is y equals, well, the coefficient from the top was 1 and the coefficient from the bottom was 3. So the horizontal asymptote is 1/3. Okay, go over to letter C. You got a degree of 1 over a degree of 2. So this is bigger on bottom. So that's y equals 0, right? Bigger on bottom, y equals 0. Look at letter D. Degree of the top is 2. The degree of the bottom is 2. So they're equal. So exponents are the same. So we divide coefficients. So y equals, the 3 is the leading coefficient on the top, and 1 is the leading coefficient on the bottom. So y equals 3. Okay, I want to go back to letter A. The reason I skipped it at first is because it's easy to tell on letter A that the degree of the bottom is 1, but what's the degree of the top? Well, if there are no x's, it's kind of like saying you have an x to the 0. So the degree of the top is 0. So this is a scenario where it's bigger on bottom. So bigger on bottom, remember, is y equals 0. Look at letter E. Would you agree this is bigger on bottom? So y equals 0. Now, letter F, you don't actually have to write this out, but you have to imagine if it were multiplied out, can you tell you would have an x squared and then some other stuff? So that's how I know the degree of the top is 2, which means this is a bigger on top, right? Because the degree of the bottom is 1. So this would be a none. Okay? So the next part, number 6, it says find all discontinuities. Well, remember what we said. Discontinuities means both holes and vertical asymptotes. So this is what we did, previously. They're saying, hey, go and find the holes, find the vertical asymptotes. Okay. I guess we'll just do one of them as a refresher, but we already did this. Okay. So just as a refresher, in order to find holes and vertical asymptotes, we need to put it in factored form. Well, on this one, the numerator does not factor, but the denominator would be x times x minus 2. Well, nothing cancels. Okay, so that means there are no holes, but there are vertical asymptotes. So what would make the denominator equal 0? Well, for the first one, it would be if x equals 0. For the second factor, it would be if x equals 2. And I know they didn't ask me on this one, but let's just add it in so we can practice everything. What if they had said, what about horizontal asymptotes? Well, for horizontal asymptotes, you're comparing the degree. I think it's easiest to compare degree by looking at the original because you can tell easily here the degree of the top is 2, degree of the bottom is 2. So this is going to be dividing coefficients. Excuse me. which would be a 3 over 1. Okay, so that's all about like horizontal and vertical asymptotes.